Hello everyone, welcome to my YouTube channel. This is me Naveen Khan from Sri Venkateswara College of Engineering, section BMW, and today I'll discuss about the topic network analysis. So starting with linear algebra in network analysis. This presentation explores the powerful interplay between linear algebra and network analysis, showcasing how mathematical concepts like matrices can be leveraged to understand complex network structures and extract valuable insights. So moving on to linear algebra fundamentals. So what are linear algebra fundamentals? These are vectors, matrices, eigenvalues, and eigenvectors. So we'll start with vectors. Vectors represent quantities with both magnitude and direction, commonly used to represent nodes in a network. And moving on to matrices. Matrices are arrays of numbers that can represent relationships between network nodes. They can be used to perform operations like multiplication and inversion, which are fundamental in network analysis. And lastly, eigenvalues and eigenvectors. Eigenvalues and eigenvectors provide crucial insights into a matrix properties, revealing dominant patterns and influencing factors in network dynamics. Adjacency matrices, representation and their properties. An adjacency matrix represents a network as a table where rows and columns correspond to nodes. Each cell indicates the presence or absence of a connection between two nodes. Properties. The properties of an adjacency matrix, like its eigenvalues, can reveal information about the network structure, including the existence of cycles and centrality measures. And moving on to matrix powers and path lengths. So matrix multiplication. Multiplying an adjacency matrix by itself, raising it raising it to a power reveals the number of paths of a given length between nodes. Path lengths. By analyzing the powers of the adjacency matrix, we can understand how connection between nodes evolve over different path lengths, and that shows us the insights into network structure. So now we'll discuss about message passing and what does message passing involves. Starting with matrix operations, message passing algorithms, fundamental in network analysis, can be implemented using matrix operations. And moving on to information dissemination. These algorithms simulate the propagation of information through a network, allowing us to study the spread of influence and understand network dynamics. Bipartite graphs, representation and matrices. Bipartite graphs represent relationships between two distinct sets of entities, like users and items in a recommendation system. Matrices. These graphs can be represented using matrices where rows correspond to one set and columns to the other. Each cell indicates the presence or absence of a connection between entities. Projection to unipartite graphs. The first one is user to user. We can project a bipartite graph onto a unipartite graph by considering connections between users who share common items, revealing user similarities. Practical applications. Influential customers and similar customers. By identifying nodes with high centrality scores, we can find influential customers who play crucial roles in spreading information or driving adoption. Similar customers. So what are similar customers? Through matrix-based analysis of bipartite graphs, we can find customers who exhibit similar purchasing patterns or preferences. Object-oriented versus matrix-based. What is the difference? So, what is object-oriented? Object-oriented approach model network nodes and edges as objects with methods and properties. This approach is often flexible but can be slower for large-scale analysis. Moving on to matrix-based. Matrix-based approaches utilize efficient linear algebra operations for large-scale network analysis. This approach is generally more scalable but can be less flexible for certain tasks. Future directions, GPU acceleration and dynamic networks. GPU acceleration. Leveraging GPUs for parallel processing can significantly speed up matrix operations, enabling analysis of larger and more complex networks. Moving on to dynamic networks, exploring approach to analyze and predict changes in network structure over time is a promising area for future research. So, thanks everyone for watching my YouTube video. This was all for today, and my topic was about network analysis in linear algebra. I hope you all liked the video. Thanks and keep watching.